The hap kit is also an impedance type haptic device. Many people like to divide kinesthetic haptic devices into two types based on how they're controlled. One is impedance and the other is admittance. First, let's talk about impedance because the vast majority of kinesthetic haptic devices are of the impedance type. In this type of haptic device, we start with user motion. The user holds onto the manipulandum or the gripper or puts their arm in an exoskeleton and moves around relatively freely. The idea being that the haptic device doesn't apply forces unless we want it to, unless we're trying to create a virtual environment. So the user can move around the workspace, and position sensors on the kinesthetic haptic device record that motion. Now comes the control aspect, where the force is computed as a function of position. So if we want to display some interesting virtual environment, we take that sensed user motion and we compute a desired force, whether it's to create a spring or a damper or other effects that we'll describe later in week 4. After this force is computed as a function of position, the haptic device itself outputs that force to the user, and the user feels the force. There is a way to close the loop from the user feeling the force back to the user creating a new motion, and that is something that's just generated based on the user's desires and on the physical configuration of their body. The key thing to note here is that for impedance-type haptic devices, this force, which is computed as a function of position, is generated by an impedance control law. So you say that force is going to be some function of position or motion. It could also be derivatives of position like velocity or acceleration. And that is the impedance type control law that we refer to when we talk about impedance type haptic devices. As I mentioned earlier, most force feedback devices are the impedance type, as is your hap kit. Admittance type haptic devices are worth mentioning, however, because they have some interesting properties and can be useful, especially when you want to display very high forces. In an admittance type haptic device, the user is thought of as applying a force rather than a position. As I mentioned earlier, there's some duality between do haptic displays create positions or displacements or forces. And similarly, you can think of a user interacting with a haptic device. Do they generate positions or do they generate forces? This is another way of looking at it. You can think of the user as displaying a force to the haptic device. In an admittance type haptic device, rather than sensing position then, you sense the force. So the device has to have some kind of force sensor. And then based on that sensed force, we compute a desired position. So rather than computing a force based on position, now we compute a position based on force. And then finally, the haptic device is controlled to output the position. For a typical kinesthetic haptic device, it's not always simple to say, haptic device, I want you to go to a certain position. That's not always going to happen perfectly. So there does often have to be some complicated low-level control which gets the haptic device to move to a desired position. And finally, the user will feel that motion. And as described earlier, there is a loop that's closed here through the human operator. When the user feels the motion, they might make a cognitive decision, a thought about how they want to change their applied force. But it's not all just about thinking. Because the user is being physically moved, that is inherently going to generate new forces. And so this loop is closed no matter what, whether we like it or not, depending on whether the user's thinking about it or not. You're always going to be closing this loop. And that's actually what makes haptic devices feel so compelling, is that it's going to feel like a real environment. This block in the middle is the admittance that's referred to when we talk about admittance-type haptic devices. And as we talked about with impedance, with admittance, we also have a function where the position is going to be some function of force. And again, this position may be velocity or acceleration, any derivative of the position or motion. And that is what is described by admittance when we refer to admittance-type haptic devices. Admittance-type haptic devices are not very common, in large part because of this issue of force sensing. Good force sensors that can make an admittance type haptic device work really well are quite expensive and they're hard to calibrate and sometimes they break. And so people often try to avoid putting force sensors on haptic devices. And I think this is one of the main reasons why impedance type haptic devices are more popular than admittance. Your hap kit actually has a force sensor on it. So it is theoretically possible to make it behave like an admittance type haptic device. And this is something that you could play with as an advanced topic, which is not part of this course. However, your force sensor on your hap kit is very cheap. It's a simple force-sensitive resistor. It's very noisy and, again, difficult to calibrate. And it's not likely that the hap kit will function very well as an admittance type haptic device. So you want to think of controlling it using the impedance type causality that's described in the previous slide. Let's review some of the main challenges in designing force feedback devices. Some of these will become clear as you do your kinematic analysis and you actually construct your hap kit. The first is that you want the haptic device to have low mass and low friction. This is because the device should be dynamically transparent. Thinking about the impedance type haptic device control, you want the user to be able to move the device around freely and only feel forces when we're trying to generate forces. So that means if the user is in an area of the workspace where they're not supposed to feel anything, you would ideally not like the user to feel the inertia and the friction of the device itself. And this is what I mean by dynamic transparency. You'd like it to almost feel invisible from the point of view of what sort of dynamics the haptic device has. Another point is that in impedance type haptic devices, the force feedback tends to feel soft. In the fourth week, you'll start to render virtual springs, and you'll see that you're going to be limited in how much stiffness you can display through these environments. This can happen because the motor saturates, so our motor is only so powerful. In fact, we don't want it to be too powerful because then it could be dangerous. Given the motor on your hap kit, you'll definitely hurt it before it hurts you. So it's not a very strong motor. Although it is strong compared to, I guess, many motors of simple robots that run around on the ground, it can't display extremely high stiffnesses. So the force feedback is always going to feel soft. Other things that limit the hardness of a virtual wall, say, that you create with a haptic device is the fact that there are very small time delays in the system. You have to measure the position, you have to compute what force to output, and then the haptic device actually has to output that force. Those small time delays also limit how stiff you can make a virtual wall because things don't happen instantaneously like they do in the real world when you interact with something hard like, say, a table. My former advisor has a great name for this lack of being able to create very stiff virtual walls, and he calls it Nerf World. The idea being that everything feels soft and squishy like a Nerf football that you may have thrown around as a kid. Another point with force feedback or kinesthetic haptic devices is that point-based interactions might be overly simple. We talked about how in a manipulandum, a grounded force feedback type device, rather than a tactile device, you are typically interacting through a single point. And this means that you're interacting with the world through a tool that just applies forces to you in one place on your body. And this may be overly simple in that it can't capture all of the complexity and depth of our haptic interactions with the real world. The hap kit is even more limited in that it only moves in 1 degree of freedom. You can get much more expensive haptic devices commercially, which will provide not only more degrees of freedom on a single handle, but even haptic feedback on multiple fingers. But even these don't capture the richness of our tactile interaction with the world. It becomes harder to feel distributed forces on the skin when you're just using a kinesthetic type haptic device. So this is not something that you can really probably ever overcome with new force feedback designs, but an inherent limitation of the mechanism. Good quality devices are expensive. The Hap Kit, although we've managed to get all the parts for you for about $50, it actually includes a motor that if it were purchased retail and not surplus like we did, costs well over $100. And often this expense comes from that motor component because it has to have low mass and low friction. And the device itself also has to be relatively stiff. You need the components, like the handle on your haptic device, to be pretty hard. Otherwise, it's not going to transmit forces from the motor very well. Another thing that causes expense is the position sensing on the haptic device. And altogether, this adds up to a pretty expensive system. The Hap Kit we can get good quality out of because it has a single degree of freedom. But if you want to have multiple degrees of freedom or even multiple fingers touching at different points and getting different types of force feedback, that just inherently increases the complexity and expense quite a bit. So we'll show some examples in the next video segment of some commercial haptic devices which range from a couple $100s to $30,000 to $60,000. There is always going to be limited workspace size and actuation power with a kinesthetic type haptic device. As you'll see when you assemble your Hap Kit, it can move back and forth over a range of on the order of 10 centimeters or so. And this workspace is going to be limited because you have a mechanical mechanism, and if you made that mechanism larger, so you had a larger workspace, then you would get higher mass and higher friction and other unwanted dynamics. And so there's this trade-off between the workspace size and degrees of freedom and this dynamic transparency that we're aiming for. As mentioned earlier, the motor can also saturate. That is, the motor may not be able to apply as much force as you like, and that's also going to keep force feedback soft and limit the kinds of haptic virtual environments that you can render. Kinesthetic or force feedback haptic devices are also usually constrained to sit at a desk. Because they're grounded, they're not something you can wear around. And even kinesthetic devices that are wearable, there's often a pack of motors that you have to wear around on a backpack. Not so convenient. So most force feedback devices today, like your Hap Kit, are supposed to sit on a desk. But at least they're kind of desktop devices and they don't fill a whole room like they might have decades ago. Finally, as mentioned earlier, there's no programmable tactile feedback on these force feedback devices. The way in which you get any distributed tactile feedback on the skin is just based on the physical handle or physical interface where you grasp the device. So you can make it feel like a stylus by physically sticking a stylus on it. You can make it feel like a thimble by putting a thimble on it. But you physically generate the tactile feedback just by whatever device you have attached to the point where the user holds the device. I don't mean to be overly negative by going over all of these device challenges, because all of these things don't necessarily take you to a point where the haptic device is useless. What these challenges do is push you to understand what are the technical aspects of what limits haptic device performance so that you can optimize within that. What it also does is helps describe, when you design a haptic device, how do you take all of the different components and design them so that they least affect things like dynamic transparency or how they affect your ability to create hard virtual worlds. So it's useful to keep all of these in mind as you assemble your Hap Kit and think about why it was designed the way it was.